Before we get started on the formal definitions of asymptotic analysis, I'd like to do a few examples that will motivate what we're going to be working on. The first example is simple linear search. Why don't you take a couple of seconds and figure out what the algorithm for linear search is. I'm searching for a variable called target that will be in somewhere in an array A. So go ahead and do that and I'll get back to you. Okay, so now here's my answer. And as you see, it's a simple loop, and we just test target against every value in the array until we find it, and then we return. So then the next question is, what's the measure of the performance? Any ideas? Well, it's big O of n because, of course, what happens is we go through this loop at most n times, and we go through that loop n times when we actually fail. If we don't fail, then we'll go through the loop fewer than n times. Okay. Example number 2. Find a variable target in either A or B. Once again, I'll give you a few seconds to think about it. You can stop the video and think about it and come up with your pseudocode, and then we'll move on. Okay, so once again, here's my solution. In this case, because we have to find target in either A or B, we'll have to look through all of the elements in A and B. If we get through this loop, that means we failed. We haven't found the target in A. And if we get through this loop, we've also failed, and we haven't found the target in B. Now, to get through the first loop, will require n iterations through the loop, and to get through the second loop will also require n iterations through the loop, and so I'll end up with 2n. And so when we ask the musical question, what's the measure of the performance, once again we'll get big O of n. For the third one, we ask the question, do the lists A and B have a number in common? Once again, pause the video, and I'll wait, and you can come back when you've thought about it. Okay, so here's my solution. In this case, this is a classic example of what's called looking for all pairs. Okay, in the sense that we have to compare every possible pair between A and B in order to determine whether they have a number in common. Now, of course, we'll stop as soon as we find that number because that's all we ask. But we do have to look at all of the pairs. This is something that happens again and again and again and again. And so we come back to the question again, what's the measure of the performance? In this case, we have an inner loop that is going to get executed n times, and then we have an outer loop that will get executed n times. And so this one is clearly order n squared. Okay. Last example. This one's a little bit trickier. Are there any duplicates in A? I'll give you a second to think about it. Okay, so here's my answer. In this case, what we have to do is we have to compare all of the pairs of A with itself. But this inner loop looks a little bit different than the others, and the reason it looks different is there's this I plus 1 there. So in the outer loop, we start with 1, but in the inner loop, we start with I plus 1 every time. And the question is why, and what effect does that have on the answer? Once again, stop the video, think about it, and see if you can come. Okay, here's one way to look at it. In this case, what you have to do is you have to compare all of the pairs in A, but what you don't want is you don't want to compare a particular element of A to itself. And so what we then do is, instead of starting with 1, we start with I plus 1. That allows us to skip to the next element in the list to start the comparisons. We also don't care if we've already compared element 1 with element 2, we don't later on want to compare element 2 to element 1. So we have to make sure that we eliminate all of those possibilities. And to do that, we start at I plus 1 instead of I. And using the binomial theorem, we get the number of times through both loops is just n choose 2. And so if you do the math, n choose 2 ends up being 1/2 n squared minus 1/2 n. And then the measure of the performance is order n squared again. But it's actually a smaller number of comparisons that we did in the previous example. Okay, so for these, in each case, we're looking for a measure of performance. The measure depends on the size of the input, and in each of these cases, we're looking at upper bounds. What's the maximum number of comparisons, the maximum number of times through the loop that we will need? So now on to the real definitions of asymptotic analysis and rates of growth.